Greetings and welcome to our tour of the Nebula Link Tool spreadsheet. The purpose of the spreadsheet is to help you design your networks and to help you pick components so that you will have a reliable fiber optic network when you're done. We'll start with a brief tour of the spreadsheet and then we'll walk through some examples in a subsequent part of the video. So the spreadsheet is designed in a simple manner. The transmitter is at the top, the receiver is at the bottom, and then your network is in between. And each field has a different function. The transmitter is where you pick the device, and if there are optical modules, which optical module you're going to use, and what wavelength the system is going to operate at. We make allowances for a patch panel, and then in this area here, you'll get into the architecture of your network. Yeah, we allow for multiplexers, splitters, dispersion compensators, amplifiers, etc. And those all run in here, and you can put them in any order so that it's quite a flexible approach. There's a field here for the number of carriers in a circuit. That is really only relevant if you're running amplifiers because it needs to know. Then we have the fiber area, and we have some choices here which we'll walk through shortly, and you get to enter your fiber length, and you can manually override certain parameters if you've got field measurements. Then there are other things that happen on the fiber. We've got field splices, repair splices, maybe connectors, and some other devices that we'll talk about later. And here again, this is the receive side of the fiber now, and again you may have a mixture of multiplexers, splitters, amplifiers, and things like that. We have a patch panel, and then we have our receiver, and again we choose a device and we choose an optical module. In this area here, you can enter your own fiber data. So if you've characterized a fiber, or if you have a specific fiber that you like to use and you know the various data values, then we would recommend using those rather than our canned responses and just put those in there. So let's start at the top. We're going to name this this link up here, and now we're going to pick a device, and we will pick ourselves a 1 gigabit head-end SFP optics device, which is our GFast. But just have a quick look at the various options that are here. We have the GFast that comes with an SFP option and a single fiber option. So if you're running a dual fiber plant or a single fiber plant, now even if you're running a single fiber plant, you could use this with a patch cord, and we'll get into that. And then the compatible units are the user interface devices. Then again, it comes in a single fiber, such as you would find in a PON network, and an SFP device, so that you would build up a CWDM or a DWDM network. So that's our gigabit device. Here we have a 100 megabit device. This one runs at 1310. This one runs at 1550. And this one is a CWDM device that starts at 1471, and there's options up to 1611. Then we have user supplied equipment. So for example, you had a router from a well-known manufacturer, but you wanted to use our SFPs, for example, you would pick user supplied equipment, and then you would get into selecting an appropriate module. Now, there's a variety of modules. There's the standard 28 dB standard band, which is 1471 to 1611, and then we have an extended band which goes down to 1271, and we have additional components which have stronger link budgets. We have a 28 dB system gain, so that's defined as the difference between the minimum receive threshold for error-free performance and the minimum transmit power of the device. Then we have 31, 36, and 41. So depending on the difficulty of your link, you have some options there. And then we have DWDM 1 gigabit SFPs of 36 and 41 dB of system gain. We have some short reach devices that run at 10 gigabits. Then we have some 10 gigabit XFPs that run either 40 or 80 kilometers. And then we have the some 1310 and 1550 rather, short and medium reach devices. So for the moment, we'll just start with that. Now we have the option here for manual power entry, so we could change that if we had a reason to. Now we need to pick a wavelength for our system to operate at. And we have a bunch of options here. If you were using the G-Fast in a single fiber mode, you can just pick that and it automatically populates that field. If you're looking at the link going the other way, then you would use, say it was the ONU end, the GFN talking to the OLT or the head end, then you would pick that device and we'll see it's 1310, and of course that is not a wavelength that is compatible with an SFP, so there's been a test check there. Now, normally if you're using modules, you would be in this range here, and we see we have extended band modules and we have standard band modules, so we will just pick a 1511 there, and we see our warnings have gone away. We're going to leave our 1 dB for the patch panel, and let's look at what our options here are for the various devices. We have a range of multiplexers, 4, 8, 14, 16, up to 17 channel multiplexers. We also have a single channel add drop mux, and we have a single channel patch cord, which is used to convert dual fiber SFPs to single fiber infrastructure. We have DWDM multiplexers, an 8 channel which lives in the 1531 CWDM band, and a 16 channel which lives in the 1551 CWDM band. And we also have patch cords for SFPs and XFPs as well if you want to run a single fiber infrastructure but are using dual fiber devices. Then we have these splitters. The splitters are for passive optical networking type single fiber outside plant, although you can use them in short reach dual fiber applications as a way of combining your transmitters. And they come in 4, 8, and 16 way. There's a multiplexer, which is a traditional WDM multiplexer, which combines 1310 and 1550. We have a hybrid multiplexer that combines 1310, 1550, as well as 1471 and 91 from the CWDM band. Then we have these amplifiers. There's a 10 dBm and a 20 dBm in this tool. And what happens is that the output level of these devices is approximately constant, and the power is evenly distributed across the carrier, the number of carriers that go into the device. So that if you were running a 4-channel DWDM system, you would enter 4 down here, and that would then take this plus 10 dBm and reduce it by 6 dB, so that you had 4 carriers running at plus 4 dBm. And there's a 20 dBm device which operates similarly. We have 2 dispersion compensators listed here, 100 and a 40. Most of the dispersion compensators run about the same loss, so if you just need one, just enter one and it'll work fine in the calculation. Of course, in real life, you'll want to buy the correct one. And then we have a no equipment option. So each of these fields is the same as that one above, and so you can put all of these devices in any order that makes sense in this area, and that'll define your transmit architecture. Now we have our fiber, and our choices here are the G652B, which is the ITU specification, your measurements, a Corning SMF28E, and then we have one field example from a local fiber that's typical of an older fiber that actually has splices and things, splices that were installed when it was built. Now we need to pick some sort of fiber. Let's just pick a generic 652B. You can also manually enter your loss per kilometer, and you'll notice again that the unit symbol moves according to the field that is active. So this field overrides that field. And then you enter your fiber length, and it gives you an estimated fiber loss, and you say, well, that's really interesting, but I already measured that fiber at 1511, and I actually know that it only has 14 dB of loss. Then you could just enter that information in, and this calculated number disappears. But we'll go with the calculated number. It's a long link. We're going to make allowances for field splices every 2 kilometers. We've allowed for a couple of repair splices. There is no multiplexer in this system right now, and there's no reason to add any additional loss or gain. And we have a receive patch panel, and we have the mating equipment, which is a CWDM 28 dB SFP. And one thing we would notice here is that, see, we've used the GFN. At the other end we have the GFL, and of course you wouldn't want that. You would want to specify the proper equipment. And so we see we have tons of margin on this link. Now that concludes the first part of our tutorial on the use of the the Nebula link budget tool with that GFast simple point-to-point example.